Hi class, so I want to do a quick introduction to section 4.2 for you. And this is about using computational geometry to place security cameras in museums. It's actually kind of a fun little problem, and I'll show you the answer and work a problem with it. All right, so let's start out like this. So suppose this is a floor plan for a gallery right here. If you stand in the corner marked A right here, so literally in the corner, the vertice right here, all right, which walls or parts of walls can you see? So if you imagine you're looking out in the line of sight, you can see this wall here, obviously, and this wall here, because they're right next to you. And as you look out, your line of sight can also tell you can see this wall. Okay, so you can see one, two, and a third, and a part of the third wall here. Not all of it, because you get blocked off past here, so you can see from here to roughly here. Okay. So the whole idea here is this, is if you have an art gallery like this, what we're going to want to do is we're going to want to put cameras in corners, okay, somewhere in corners so that we can see all the floor plan, so we can have it all covered and monitored. All right, so the question is what's called the Kiel Art Gallery question. So for an arbitrary polygon closed curve, so going back, this is a polygon closed, okay, because each side is a straight line and it's closed all the way around, okay. All right, in the plane with V vertices, so what those V vertices are these turning points right here. How many vertices are required such that every point in the interior of the curve is visible directly in the line of sight from at least one of these chosen vertices? So modifying this question, it's kind of like for an arbitrary gallery with having V corners. So V is like, how many corners does this have? Okay. Um, So looking back here, this is a corner, this is a corner, 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 and a corner. So it looks like there's 1, 2, 3, 4, 5, 6, 7, 8, 9 corners. Okay. How many cameras are needed to ensure that every point in the gallery is seen by some camera? Okay. Well, it turns out the theorem tells us the answer to that question. So suppose we have a polygon closed curve in a plane with V vertices, like 9. Okay. Then there are V divided by 3 vertices from which it is possible to view every point on the interior of the curve. Okay, so if you take 9 divided by 3, what you could do here is you could put a camera. Remember, there's um, 9 corners. Okay, so you take 9 divided by 3. What I'm saying here is you could put 3 cameras in here to cover every corner. You could actually put a camera here, and a camera here, and by line of sight you could see everything. All right, if v divided by 3 is not an integer, then the number of vertices we need is the biggest integer less than v divided by 3. So for example, if this would be 10 divided by 3, 10 divided by 3 gets you 3.33333, you would still just need 3. All right, let's work a problem that looks a lot like a question on your homework, okay? So the problem here is you have this. At what vertices would you place cameras so that you use as few cameras as possible so that each point inside the curve is visible from a camera? Well, the first thing you have to do is count the number of vertices. So we'll start here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so 12 divided by 3, that tells me I would need 4 cameras. And the trick with something like this is you would place one here. Like I'll just show you. You place one here. Then what you'd have to do, this would see your line of sight from here down to here and so on. You would place one here to catch the other side. You would place one here. And you would place one here. And that right there, okay, would be how you could cover every single thing with 4 cameras. Okay. Well, I hope that helps, class.